Hi everyone, welcome to the next video. This one might be a little bit long. There are a few slides to get through, but there's not actually that many questions, and all the questions are kind of similar, so hopefully we can get through it pretty much okay. So far we've talked about the gravitational field, what it is, how we can describe it, its shape, things like that. And we've also discussed how it can also be thought of as a way to talk about the force that an object would feel per kilogram that the object contains. All right? So that's what the units of the gravitational field tell us. In this video, we're going to look at how we can actually calculate that force. Okay? I'll give you a couple of equations. One of them is not actually written down strictly in the notes, but it was looked at previously in one of the other videos, in one of the other sections of the notes. So go back and watch that video. I think it was the first one, or actually the second one, when we talked about calculating the gravitational field strength. Okay, the formula was F equals mg. Basically, okay, and that's just the normal force that you're used to calculating when you deal with force problems, and you've got to calculate the gravitational force that an object experiences. This little g now, instead of being 9.8 just as a given, g is the way that you, g is the gravitational field strength, and we calculate it using g equals big G times the mass over r squared, where m here is the mass of the object that's exerting the field, not the mass of the object that we've placed in the field. Okay, so just be aware of that. So we're talking today about how to calculate the gravitational force. So that's one equation. You'll see the other equation in a second. Here's our key knowledge focus. So this is the second part of this particular dot point, where we're looking at how masses accelerate due to gravitational fields in the context of looking at the force that the objects experience. Now, this is an interesting equation. Let's look at it a little bit more in depth. So here's Isaac Newton with my little drawings on him. Isaac Newton was pretty much the first person who really delved into what gravity is. Now, he didn't give an exact mechanism by which gravity is transferred from one object to another. He just said gravity is here, and this is how we calculate it. Basically, that's what he described through a series of experiments. Okay, and what he said was, through the course of his experiments and through the course of his observations, he says, any two bodies in the universe attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of their distance. Okay, now what we can do is sum all that up in a formula, and it's basically this formula here. Okay, so product directly proportional to the product of their masses. So the force is equal to some number, which we've seen before, multiplied by the product of the masses of the two objects. Okay, but it is also inversely proportional to the square of their distance. So we need to divide all of this inverse by the distance between them squared. Okay. We've already seen this inverse proportionality pop up when we looked at the how we calculate the gravitational field. So you should be familiar with that. All the other part is saying is that if you double the mass, you double the force. Okay, if you double one of these masses, so instead of m1 times m2, you might replace m1 with 2m1. All that means is that because you've multiplied basically this entire right-hand side by 2, that means the force is going to double. Okay, so doubling either of the masses will double the force. Doubling the distance between them will reduce the force to a quarter, and that's the inverse square rule at work there. We'll look at it again in a little bit. Okay, so that's our equation in full. Fg, gravitational force between two objects, okay, measured in newtons, obviously. M1 and M2 are the masses of the two objects, or the two bodies, and they are measured in kilograms, like normal. R is the distance between the center of masses of the two bodies in meters. And G, this big G here, this gravitational constant, again, is 6.67 times 10 to the negative 11. Don't worry too much about the units. It's just to make the equation work. So, I mean, it kind of looks pretty similar to the way that you calculate little g. The only difference is, in the little g formula, you've only got one mass, okay? And now if we were to try and calculate the force that another object would experience in this particular location of the gravitational field, you would just then multiply the mass of that other object by g. Okay, so F equals mass times g m on r squared. You can put that mass up here in that fraction, and you get g times m times m over r squared. Okay, and that's basically this equation. Okay, so what the equation is saying is that one of these masses is producing the gravitational field. The other mass is the mass that's experiencing the force due to that field. Okay, but you can just as easily swap those two masses around in the formula, and you can say that mass number 2 is the one that's creating the field, and mass number 1 is the mass that is experiencing the force due to that field. Okay, because you've got to remember Newton's third law. If one object pulls on another object with some force, then the second object also pulls on the first one with the same force. Okay, so it doesn't matter what order you multiply those masses, the force between them is going to be the same. All right. So let's just apply that equation to a question. So here we've got a man with a mass of 90 kilograms and a woman with a mass of 75 kilograms have a distance of 80 centimeters between their centers. Calculate the force of gravitational attraction between them. Okay, so this is simply just asking for force between two objects with a distance between them. You just go ahead and apply your formula. Okay, that's our formula. G 6.67 times 10 to the negative 11. Mass number 1 is 90, mass number 2 is 75, and the distance between them is 0.8 meters. And you've got to square that, don't forget the squared, and also convert your distance to meters if you need to. And popping that on a calculator, you end up getting something very, very small. 7.03 times 10 to the negative 7 newtons. So it's a tiny force, okay? That is not even a millionth of a newton, okay? So that's why you don't go around feeling, gravitational attraction towards objects while you're walking down the road, okay? The force that you would try and experience there is tiny, okay? And then if you were to work out acceleration, it'd be even tinier. Actually, that's not true. If your mass is bigger than 1 kilo, then acceleration is going to be... Actually, no, that's wrong. What am I saying? Forget what I just said. Forget the last 10 seconds, okay? It's a tiny force. You don't go experiencing that in everyday life, all right? So there you go, okay? Simple question, just apply the equation, pop in your numbers, just make sure the values are in the right units, and don't forget the square here. All right. Okay, so we're going to talk again about the inverse square proportionality. All right. So we talked about this in the video for gravitational field strength. We're going to talk about it again here. All it's saying is that, if you double the distance that you are from an object, then when you expand this out, you end up getting 1 over 4 r squared, which you can write as 1/4 times 1 over r squared, which would have been your original fraction. So your new force is 1/4 of what it originally was. That's how that works, okay? And it also works in reverse. If you were to halve your distance, then what you'd end up getting is 4 times the original fraction, okay? So that's all that's saying. So you can go back and watch the field strength video again. I'm not going to go through it too much here. Now, again, we've also got to talk about the attractive nature of gravity, okay? We say that the gravitational force is always an attractive force. So things will not get repelled, things will just sort of gravitate towards each other be attracted towards each other and start accelerating towards each other, okay? Now, there is some theory and some talk about the fact that because we think the universe is accelerating in its expansion and that things are sort of flying away from each other, there's got to be something causing that, okay? So it's hypothesized that there's this dark energy somewhere out there in the universe that's sort of acting as an anti-gravity kind of situation. You don't have to remember that. It's not part of your study design. It's just something interesting to know. Also, you've probably heard of antimatter. So, for example, the antimatter equivalent of an electron is a positron. Okay, so that's when those two things combine, they annihilate and you create some energy. It's not actually understood or known whether antimatter possesses like a repulsive gravity of any kind. We actually don't know. All right, so you can go and read up on that if you want. Again, you don't need to know that for your study design. It's just something interesting to know. Also, last point here. So the gravitational constant, big G, is really, really tiny. Okay, remember it's 6.67 times 10 to the negative 11. So when you multiply your force fraction, I guess you could call it, by this tiny number, it ends up making your force much, much smaller than, say, the electric force, which we'll study later on, which has basically an equivalent sort of constant, except it's something like 9 times 10 to the power of 9 or something like that. I can't remember the power. But it's much larger than the gravitational constant, okay? So gravity is one of the weakest of the 4 fundamental forces. In fact, it is the weakest by quite a large margin. The 4 fundamental forces being the electromagnetic force, the strong force, the weak force, and gravitational force. Okay, you can go and read up on those 4 forces if you like. You don't really need to know about them here. All right, so just know that gravity is really weak. Gravity is always attractive, and it gets weaker and weaker as you go away because of the inverse square law. That's all this slide is saying. Okay, let's do another question. So calculate the gravitational force of attraction between the Earth and the Moon using the following data. Again, it's just a do this, plug in this type of question. Okay, so force equals G times M1 times M2 over R squared. So we've got 6.67 times 10 to the negative 11 times, all right, mass of the Moon. Let's do that one first. Times the mass of the Earth. All divided by the distance between them squared. So you might want to put that in brackets on your calculator just to make sure that you're squaring what you need to square. And you end up getting something on the order of 2.02 times 10 to the power of 20 newtons. So it is quite a large force, okay, and that's kind of to be expected because the masses of the Moon and the Earth are so big. Even though the distance between them is pretty small, pretty large as well, so this fraction would end up being, quite small in the grand scheme of things. It's just that the masses are so huge that it still ends up being a massive force. Right? Now, if you were to go ahead and calculate the accelerations of the Earth and the Moon, that's another story. Okay, and the accelerations are what matter when you're talking about the motions of things. The force doesn't matter because it depends kind of how big the thing is you're applying the force to, yeah? So you can calculate the accelerations of the Moon and the Earth if you want, just to see how their motion is affected by the gravitational force here. Right, so this brings me back to what I was kind of talking about when we introduced this equation. Gravity is a force, okay? So we know from Newton's third law that for every action or for every force, there is an equal but opposite reaction or an opposite force. So if you think about it, I mean, the Earth is getting pulled around by the sun. Okay, there's a force of gravity between the Earth and the sun. But that also means that the sun is being pulled a little bit by the Earth. Okay, now because the sun is so much larger than the Earth, you tend not to notice that effect. Okay, So what's actually going on? Let me draw a picture just of the Earth and the Sun. Okay, so here's the Sun. If my stupid pen decides to draw. Here's the Sun. Here's the Earth. Okay, don't worry about the distance. It's much smaller here than what it actually is. Now the Earth would go around the Sun, something like that. Okay, in what we call an ellipse. We'll talk about that later on. You can consider it basically a circle, so that's a pretty crappy circle. But the Sun goes around the Earth as well. Now, when I say goes around the Earth, I don't literally mean it goes around the Earth. That two objects actually orbit a center of mass. Okay, so the Earth is going to orbit this center of mass, which is basically probably somewhere inside the Sun itself. So I'm going to say the center of mass is there, because the Sun is so much more massive than the Earth. The center of mass must be closer to the Sun in order to keep things balanced out. So the Earth is actually orbiting this point here. It's not actually orbiting the Sun, right? But the Sun itself also orbits this point here. Okay, so we don't notice that because the point is so close to the Sun. But if you were to sort of zoom out and observe things from a distance, you'd notice the Sun sort of wobbling around. Okay, and that's due to the fact that the Earth is pulling on the Sun. Okay, it's not just the Earth that's moving around the Sun because of gravity. The Sun is also being moved because of the Earth, and that causes it to wobble. Okay, it just doesn't wobble as much. It just doesn't move as much as the Earth does. Okay, because it's so much bigger. Right, it's like saying, here's a truck that weighs a billion kilograms, and here's a leaf that weighs 0.5 grams or something stupid like that. Let's push them both with the same force. Which one's going to move more? Obviously the leaf, because it has less mass. So that's kind of what's going on here. All right. So question 9. The force of gravitational attraction between the Sun and the Earth is approximately 3.6 times 10 to the 22 newtons. Calculate the acceleration of the Earth and the Sun caused by this force, and compare the accelerations by calculating this ratio. So how do we calculate acceleration if we've got force and a mass? Well, you just use Newton's second law. Acceleration equals force divided by mass. So let's do the Earth first. Calculate how much the Earth accelerates due to this force. So I'm going to do 3.6 times 10 to the 22 over 6 times 10 to the 24. And you end up getting a pretty small number, 0.006 meters per second. All right, so that's not bad. Okay, it's small, but, you know, give it enough time, it will reach a large enough speed. Let's talk about the Sun. What is the acceleration the Sun experiences due to the force that the Earth is exerting on it? So, same force. Okay, Newton's third law, same force between two objects. But the mass of the Sun is much bigger. 2 times 10 to the 30. Plug that in your calculator and you get a very tiny number, 1.8 times 10 to the negative 8. That, sorry, should be squared here. Meters per second squared. Okay? Now already you can tell that the acceleration of the Sun is much, much smaller than that of the Earth. And that's why you don't notice the wobble of the Sun. But if we were to calculate that ratio, AE divided by AS, approximately equal to 3 times 10 to the 5. Okay, so the acceleration of the Earth is around 300,000 times more than that of the Sun. That's what that ratio is saying there. Okay, that's why you notice the Earth going around the Sun, when actually, in fact, it's going around a center of mass that's close to the Sun, because the Sun is also accelerating. It's also moving in a elliptical or roughly circular path. Okay, it's just the path is not as big. All right, so just remember that. Okay, last question for this video. So it says the gravitational force between two objects is F newtons. If the distance between the objects is doubled and the mass of one object is tripled, what is the new force between these objects in terms of F? Okay, so we know that F is proportional to the product of the masses divided by the square of the distance between them. Yeah? That's our proportionality. That's what Newton first sort of described when he talked about gravity. Okay, and if you wanted to make it an equation, you'd need some kind of constant to make the proportionality work, and that would just be big G. Okay, so let's modify these values and see what pops out as a new force. So it's saying that we are doubling the distance between the objects. So we're saying the new force is going to be sort of equal to or proportional to, if we just ignore G. It's going to be, so the distance is doubled. So we've got to replace R with 2R. And one of the masses is tripled. So let's say mass 1 is tripled. We just, instead of writing M1, you can write 3 times M1. Okay, and we're still keeping the second mass the same. What we want to do is try and simplify this so that we get this fraction out multiplied by something else. Okay, so watch how I do this. We can keep the 3 up there for now, times M1 times M2. In the denominator, if you expand this, you end up getting 4 times R squared. And then what I can actually do is separate this fraction with these numbers out from the original fraction that we've got to begin with. Okay, so this thing here is what we started with over here, but this is now the new force. Okay, so what this is actually telling us is the new force is 3/4 the strength of the old force, because this quantity here is basically the old force. Okay, that's what we started with before we modified our numbers. Okay, so the new force is equal to 3/4. That's what that fraction here is implying of the old force. So 3/4 times F. Okay. So that's how we deal with these kind of proportionality questions. If you're modifying one or more variables in your calculation of the force, you can just do it like that. Try and rewrite this new fraction after you've modified the values in terms of the old fraction multiplied by some number. Okay, and that will tell you the factor of which your old force has changed into the new one. Okay, so here's our summary. This is what we did today. So we talked about how Newton made up this law about how gravity, how the strength of gravity works. He came up with the fact that gravity is proportional, directly proportional to the product of the two masses of the bodies that we're talking about, and inversely proportional to the square of the distance between the bodies. That's what that's saying. Okay, just remember it's an inverse square law. Okay. He didn't tell us a way that gravity worked. He just said, here is a way to predict the force of gravity between two objects. Okay, so it's a predictive sort of law. It doesn't really sort of explain why things experience gravity. For that, we need to talk about the field. Okay, and if you want to get more in depth, then you use general relativity. Okay, so you only did this as a way to predict the force, not to actually explain why gravity exists. Anyway, here's some summary questions. Try and answer these yourself. These are sort of just theory-based questions. Try and write a little explanation for each one. You can check the OneNote for some suggested answers. Okay, and that's it for this video. Sorry about the length. There was a little bit to get through, but that's it pretty much for force. We'll talk a little bit about weight. So the force due to gravity as termed as weight, and how we can talk about apparent weight, apparent weightlessness, and true weightlessness, and how all these things are sort of related. Okay, that's in the next video. So I'll see you then. Goodbye.